Thank you for the opportunity to speak in this seminar. So, as you mentioned, this is part of my PhD project. Specifically, there's two papers underlying this talk. One of them is on arXiv, the other one will be available on arXiv tomorrow. Yeah, and it's entitled Efficient Nested Information Estimators for Expected Information Gain. And my co-workers are Andre Carlo at KAUST, Louis Espath at the University of Nottingham, Sebastian Krumscheid at the Karlsruhe Institute of Technology, and Raoul Tempone at KAUST and RWTH Aachen. So we start off by introducing the data model, where we have observation data Y and a forward model G that depends on the true parameter of interest that we call theta T. And we have additive observation noise, epsilon. And we will assume that this is coming from a centralized normal distribution throughout this work. Yeah, and from this model, we will build the more elaborate things that we want to present. So we start off by a simple example so that everyone can kind of get some picture of what this means. So we have here a electrical impedance tomography. We have a composite laminate material, meaning that we have two plies here. I hope you can see my pointer. So we have two plies that have a fiber structure, and we have electrodes. So the red electrodes are inlet electrodes, the blue one are outlet electrodes. We inject electric current, and then we can measure the current. And this way, we can generate an image of the interior of this domain. So for us, the observation data is voltage measurements at the electrodes. The theta true, the parameter of interest, is the fiber angles in the plies. And the G is the solution to a partial differential equation. And as I already mentioned, the observation noise, meaning that our measurements are not perfect. We assume measurement noise with a known covariance matrix. So there's 10 electrodes, only nine-dimensional output. So basically the 10th electrode is given as a boundary condition. So this is why we have 9-dimensional output, basically. And yeah, if you have any questions, you can always interrupt and ask or wait for later. And okay, so the next thing is we can solve an inverse problem. So the forward problem is basically we have a parameter of interest, and then we can solve the PDE and we get the measurements, basically. The inverse problem is if we have measurements, we want to recover which parameter generated these measurements. And we can do this using least squares, given in this form, where basically we want to find a theta that matches the observation. And this provides a point estimate of theta true. The issue with this is that somehow the uncertainty of not knowing the actual theta true will be lost in this. So we get some value for theta that we assume is most likely to have generated the data, but we're not sure how good this estimation is really. So then we can introduce the Bayesian inverse problem, where we assume a random variable theta to model this uncertainty about the true parameter of interest. What do we mean by Bayesian inverse problem? We assume a prior distribution of this theta. This is what we know before doing the experiment. So basically our assumptions or knowledge from previous experiments or expert knowledge, some physical constraints. Then we have the posterior distribution, which is conditioned on the observation. And we have the likelihood, which is the likelihood of observing data for a given theta. It's given as a normal distribution, where the mean is the model output. And finally, the evidence, which is just the probability of observing data, which is not given directly, but rather through marginalization. And the posterior is given by Bayes' theorem as the likelihood times prior over the evidence. And this is then the solution to the Bayesian inverse problem. So now it's not a point estimate. It's a probability distribution telling us how likely is each theta. And this also tells us how is the uncertainty after the observations. Okay, so again, for our now slightly different model where we have this exclusion as well, that we can model. So now we assume that our we assume prior distributions for each parameter of interest. So the first parameter of interest is the fiber angle in the top ply. We cannot see it here anymore, but yeah, there were these two plies, and now we have an exclusion between the plies. Theta 2 is the fiber angle in the bottom ply, and theta 3 is now the vertical axis of this ellipse. Yeah, and these we assume are given by some uniform distribution, and then we can solve the Bayesian inverse problem after observing data measurements and obtain a posterior distribution.
I'm sorry, Arved, one small question. Where did you take these numbers? Did you try many different numbers and let's say 006 or 007, and by some reason you come to these numbers? How many preliminary tests you did to come to these numbers, which we see here?
For the fiber angles, we took these numbers from our previous paper from our group. So I did not experiment with this. For the theta 3, yes, I experimented a bit. For these third numbers, yeah, but not.
So did you observe something negative if you take another numbers? Let's say 0.5 for theta 3 is too much already.
No, I mean, if you sample from the uniform distribution directly, then you will always get something in here. Of course, this can't be negative because the vertical axis of the ellipse has to be some positive number, and it should not go outside of the domain. So it should be somewhere between 0 and 1. But no, yeah, I think this works for pretty much anything between 0 and 1. And we just took this to get some, some reasonable amount of uncertainty here.
Okay, thank you. I'm satisfied.
And this is mostly for visualization. We have another work where we reduce this drastically so that it's really a thin exclusion. So basically, yeah, much smaller. And then, yeah, we may have issues here later on, but I will get to this hopefully. But with the uniform distribution, no, we did not encounter any issues here. Okay.
Thank you.
Welcome. Okay, so now the next part is we want to design experiments so that the observation data we get will be more informative. So we introduce a design parameter and now say that this is our data model where G now depends on the theta true and the design psi. And we also repeat the experiment several times. So we have now NE number of experiments. So we have the same model, the same setting, the same experimental setup. We just run it several times. So we have multiple observations. The only thing that changes is the noise, which we cannot observe directly. And then we write all the observations from all the sensors, all the electrodes, and all the experiments into one big matrix, basically Y. Yeah, and these measurements depend on the design. And then we want to define this design psi, which produces the most informative Y. So again, for our electrical impedance tomography experiment, what this means is we can move around these electrodes. So you see that here on the top, we have a small shift here between inlet and outlet electrodes. And on the bottom, we have a large shift, but only a small distance between the electrodes. And here we have a large distance. And what this does is it changes the current flow, as you can hopefully see in this figure. And this, of course, influences the measurements we will get at the electrodes. And this means that the data will change, and then we can more easily or not as easily recover the parameters of interest. So yeah, psi1 is this shift that I mentioned, and psi2 is the distance. And yeah, we basically want to find the electrode setup that lets us optimally recover the parameters of interest. Okay, and now what does it mean? How do we quantify the informativeness of the data? We have the Kullback-Leibler divergence between the posterior distribution and the prior distribution, where, again, the posterior distribution here is our knowledge or our information about theta after observing y, and the prior is our knowledge about theta before the experiment. And we want to do all of this before the experiment because we want to find the design that gives the most informative experiment. So we have to do it beforehand by modeling it and running simulations. And then, but this is for a specific observation set y, but we want it for all possible observations. So we take the expectation over all y's, and this is known as the expected information gain. And then we apply Bayes' theorem to rewrite this as the likelihood and the evidence. And then we use the marginalization so that now everything is in terms of the likelihood and the prior. And we have access to both of these. As I mentioned, the prior is assumed and the likelihood is given by this normal distribution. And here I introduced a var theta to distinguish from the outer theta for integration.
I'm sorry, small question. Why Kullback-Leibler divergence and not some other, any particular reason for this?
Basically, there could be any sort of function that somehow relates the input parameters and the data. But I think it is mostly accepted now that the expected information gain is one of the most useful or practically applicable utility functions, as it's called, for experimental design. Yeah, it is one of the hardest to estimate, basically, and this is what I would show how to estimate this quantity.
Okay, thank you.
Welcome. So the issue here is that we have what we call nested integrals. So we have one large integral out here over theta and y, and then we have the logarithm and another integral in here, also over theta. And this makes numerical approximations challenging. So having one higher dimensional integral out here is not that big of a deal. We will use Monte Carlo methods, which do not suffer from the curse of dimensionality. And actually, this first part is also not a problem. In fact, it's given in closed form. But this inner integral is usually not given in closed form. So we have to use some approximation scheme that can approximate these nested integrals. So now I will briefly introduce how to estimate standard integrals numerically. So we have, as you're probably all familiar, a very basic form. We have the unit hypercube in t dimensions. We have some integrand g of a vector, a variable x. And we can approximate this integral by taking a finite number of evaluation points, xm, capital N points, and this approximates the integral as m increases. Okay, the Monte Carlo estimator uses IID points, independent and identically distributed points from the uniform distribution in d dimensions. Or we can use quasi-Monte Carlo, where now the points come from a deterministic low discrepancy sequence. There's other methods, of course, as well, deterministic quadrature, and so on. But these two will be the ones that we focus on in this talk, with some small caveat that I will get to in a second. Okay, and if we want to integrate over a general domain instead of the unit hypercube, we can transform the integrand, we can apply the inverse CDF of some other distribution, and then, yeah. But basically, this is a form that we can write the integral. Okay, so introducing the Monte Carlo estimator with the IID points. This estimator is unbiased. So basically, the expectation of this estimator for any number of samples will be the true integral. And this is easy to see because all the points are as good as an estimate as every other point. and it has a variance. And we can show by the central limit theorem that the statistical estimator, so basically the probability that the error of the Monte Carlo estimator is below this epsilon, this Monte Carlo error, is larger than this probability for a confidence parameter alpha. We can choose this alpha very small, then we have a high probability of a small error. And this Monte Carlo error now is given by 3 components. Basically, we have this confidence constant C alpha that depends on alpha. We have the standard deviation of the variance of our integrand and the square root. So yeah, and we have the square root of the number of samples. So basically, this confidence constant, we will assume it's fixed. If we choose alpha equal to 0.05, this C alpha is given by 1.96. It's the inverse CDF of the standard normal. And of course, if we want to reduce this error, we can always go the hard route and increase the number of samples. And this should be obvious. As m goes to infinity, we approximate the integral. But this, of course, increases the cost of the estimator. It's not very efficient. And it's kind of a brute force method to reduce the Monte Carlo error. So what we will do instead is we try to reduce the variance of the integrand. And there's many ways to do this. And yeah, this is the focus of our work. And this also reduces the Monte Carlo error, hopefully more efficiently than just increasing the number of samples. And for the quasi-Monte Carlo estimator, again, we have the same shape, except that the evaluation points x come from a low discrepancy sequence. But the error is hard to estimate. So there are error bounds, but first of all, these error bounds are sometimes as challenging to estimate as the actual integral, and they may also not be tight. In fact, they may be infinite when the actual error is finite. So these are not very practical. What we do instead is we use randomized quasi-Monte Carlo. And the randomized quasi-Monte Carlo estimator basically means we use low discrepancy points and then randomize all the points. And this way we can use the central limit theorem again. So this outer randomization is basically Monte Carlo of the quasi-Monte Carlo estimator. And this error is much simpler to estimate. It is again unbiased. The non-randomized quasi-Monte Carlo estimator would not be unbiased, since all the points are deterministic, but this one is unbiased. We can show it here. It's basically the same derivation as before, because every individual point is now again a uniform random variable, but they are not independent. They all know about each other. And the statistical error now in the central limit theorem is given here again with the confidence constant, and now with the square root of r, the number of randomizations. And here we have the sample variance of this quasi-Monte Carlo estimator. So what's the difference now to the Monte Carlo estimator? The advantage we have is that this variance estimate decreases with the number of m, the number of low discrepancy points. And it decreases at a faster rate. It's not 1 over square root of m, or m to the minus 1/2, it's m to the minus 1 plus delta. And so this is the variance. Before I had the standard deviation. So m is basically for Monte Carlo, m is minus 1. And for quasi-Monte Carlo, it's minus 1 plus delta, where this delta is between 0 and 1. And this delta depends on the dimension and on the regularity of the integrand. So basically, if our integrand is nice and the dimension is not too high, we can use this to our advantage and obtain a quasi-Monte Carlo error that decreases faster than the Monte Carlo error. Okay, so now how do these points look like? The randomized quasi-Monte Carlo points depend on a deterministic component. This is the low discrepancy point, now called zeta, and a randomization. And the randomization also depends on which points you choose. There's different low discrepancy sequences that you can choose from. I will not go into detail here, since it's not the main focus of our work, but yeah, just to give some visualization. These are random points, and we can see that there's clusterings here, and then there's areas where there are no points, meaning that we have sometimes large areas where we have no clue of what our function does. And this yeah, basically causes this rather slow error convergence of rate 1/2. Then for this one low discrepancy sequence, it's called rank 1 lattice rule. And these are the deterministic points. So we can see that they fill the space nicely. The first point is always at the origin. Yeah, and they are not quite a standard lattice, meaning that, for example, we have here 16 points in 2 dimensions, and we have 16 distinct x values and y values, basically. So in each dimension, we have distinct values. If these were a regular grid of 16 points, we would have, if we basically project to this dimension, we would have 4 distinct points, and to the other dimension also 4 points, meaning that yeah, we would have basically the same function evaluations in each dimension multiple times. Okay, and now this means that they are at the same time more useful than random points or to standard lattice points. And how do we randomize those points? We add, so we sample a random vector here, shown as this red arrow, and we add it to each point. The same randomization, so we take all the points and move them all at once. And if we were to move a point outside of the domain, we wrap it back around and put it in here, and for this side as well. And this guarantees that all the points stay inside the domain. So here finally we have the randomized points for one randomization, and they still have the low discrepancy structure. They still cover the space well, and at the same time each point is now a uniform random sample. And we are no longer at the origin, which might cause issues. For example, if we transform to normal distribution. Okay, a different point set that we will actually use are suball points. The idea here is also to cover the space well. So on the left, we have the deterministic suball points. It's a bit harder, unfortunately, to visualize the randomization that is used here. But basically, you can see that the idea is, okay, we have 16 points. The first one is again at the origin. If we split this in half vertically, we have 8 points on the left, 8 points on the right. If we split horizontally, we have 8 points on the top, 8 points on the bottom. In the lower left box, we have 4 points, top left 4 points, and so on. So basically, we split the interval in each dimension into smaller boxes or smaller intervals. And then we should have the same number of points until we run out of points. Of course, for 16 points, we will have an area here, but there's just not enough points to fill every box. And then for the randomization, basically, we imagine this split here, and then we apply a random permutation. Either we keep the left and the right side as it is, or we switch. We just move all the points on the left to the right and vice versa. And then we split again, basically into quarters. So each of these intervals we split again, and to each left half we again randomly permute or not, and on the right side as well, and so on. And this goes on until we run out of machine precision, basically. And then we do the same in the other dimension. So we split in top and bottom. Either we permute top and bottom or not, and then we split the top in 2 and the bottom in 2, and we permute each of these and so on, so that at the end, every point will be a uniform random variable. But we still have this property that in every sub box, we still have 1 point each, or at most 1 point, with probability 1. Okay, so these are the suball points. And yeah, as already mentioned, the Monte Carlo error is m to the minus 1/2. the randomized quasi-Monte Carlo error is r to the minus 1/2. R are the number of randomizations, and m is this minus 1 plus delta over 2. Because in the error, as you remember, we have the square root of the variance. Okay, so now from this we can see it makes no sense to increase r. And it's always, since delta is between 0 and 1, it's always better to increase m, since we get a better error convergence, and the cost is the same whether we increase number of randomizations or the number of points. So this is linear in the cost. The only reason we do this randomization is to get an error estimate, because the central limit theorem is only valid in R, not in M. So we have to hope here to get a large enough R to get a credible error bound. But we will keep these fixed at, we use 32 randomizations. Some people use 10 randomizations. Basically, this is some hyperparameter that you have to choose, but it makes no sense to let R actually go to infinity for the actual estimator, only for the to get an estimate on the error. But then we increase M and we get this better error convergence. So the optimal work, if we introduce an error tolerance tau that is larger than 0 but fairly small, we can compute the optimal work of the Monte Carlo estimator is tolerance to the minus 2. You can see this clearly from up here. If the error is m to the minus 1/2 and the cost is just the number of samples, it's basically 1 over tau squared. And if we keep the number of randomizations fixed, the work of the randomized quasi-Monte Carlo estimator will be tau to the minus 2 over 1 plus delta. And this means for delta 0, we get the same work as for the Monte Carlo estimator. For delta is 1, the work is 1 over tau. So this is much more efficient and basically also optimal already. It's usually not possible to estimate integrals with a cost of which is better than 1 over the tolerance. Okay, what I did not mention yet, but I hinted at the beginning, is that we usually don't even have the integrand directly. We have to solve a partial differential equation. We have to use finite elements, or in other applications, finite differences, or some other numerical discretization. And we call this GH, where H is a discretization parameter. And then we have the weak error with the weak error rate eta, which we call eta. And this also introduces a cost. And the cost is proportional to h to the minus gamma for some positive cost rate. And this, if we use the discretization of the integrand, this adds bias to the Monte Carlo estimator and the randomized quasi-Monte Carlo estimator. And this increases the cost. So now the cost of the Monte Carlo estimator is the tau to the minus 2, as we had before. And also this finite element cost. And the same cost is added to the randomized quasi-Monte Carlo estimator. Okay, so using the quasi-Monte Carlo points was one way to reduce this variance and therefore reduce the error and improve the cost. Another way to reduce the error of the Monte Carlo or randomized quasi-Monte Carlo estimator is to use importance sampling. And these are basically the two techniques that we will later use. So importance sampling means that we change the integration measure. So now we have our integrand G and some integration measure P, and we just multiply and divide by some new measure Q. And then for the sampling-based estimators, we sample from this new measure. And of course, we have the same integral, so we don't add bias, but hopefully we can reduce the variance if we get a good measure Q. And to get a good measure Q, we need some knowledge of our integrand, basically. And one way to get this is our method of choice to obtain this important sampling measure Q is Laplace's method and the Laplace approximation. So what does it do for those not so familiar with Laplace's method? if we have an integral that is of this form, so e to the minus then some constant d times g of x for a positive function g, we can approximate it using second order Taylor. So we do Taylor approximation in g of x around the point x hat, and x hat will be the maximum of g. And since it's the maximum of g, there's a constant term but no linear term, as you can see here, because the linear term will be 0 at the maximum. And then we have the squared term. And we can pull this first term out of the integral since it's independent of x. And the second term is now a Gaussian integral. Basically, this is a multivariate Gaussian distribution in x, and we can solve it in closed form. So this is given as this here, as I'm sure you're all familiar. And this holds as d goes to infinity. And as I said, the x hat, the evolution point of the Taylor approximation is the arc mean of g, or the maximum of minus g. Okay, now how does this look like? Yeah, and okay, we have the Hessian here also, so we need to approximate the Hessian of g and assume that okay, g has an actual maximum and that g is positive definite at this maximum. So those are the assumptions we need on our integrand. How does this look like? We have an example here. G is given as this e to the x minus e squared over 2. And here in blue, we have this function, right? And the red one is basically our Gaussian approximation. So we can see that for d 0.1, for a very small d, it's not very accurate, but we capture at least we capture the maximum correctly. And then as we increase d, this approximation converges to the true integral. And this approximation converges at a rate 1 over d squared. Basically, okay, for this example, it's not perfect. I used the Gaussian quadrature because the actual integral is not given in closed form. So yeah, but basically this converges as d increases. Now I will talk about this later, but d is not as easy to just increase as, for example, the number of samples. D is usually fixed for our purposes. So yeah. Okay, and then we have the Laplace approximation, which is often used in Bayesian experimental design, where we can now approximate the probability density, which often has this type of shape with a normalization constant. So the normalization of this is given by the integral over the whole domain. And then we use basically the second order Taylor in both the numerator and the denominator. So in the denominator, we have the standard Laplace's method that I just introduced. And in the numerator, we also use the same second order Taylor. And then we can again evaluate this integral in closed form. And this is now a normal distribution, and it has this shape. So it's a Gaussian with mean x hat. Remember, x hat is the maximum. So basically for a probability density function is now the map, the maximum a posteriori estimate. And the covariance of this Gaussian is the d times the Hessian evaluated at the map inverse. Yeah, and this is called Laplace approximation. And this now we can use for important sampling. And this hopefully will reduce the variance of Monte Carlo or randomized quasi-Monte Carlo estimators, sometimes as numerical experiments show drastically. And what we need to use this is we need to estimate usually numerically both the x hat and the Hessian. But this is yeah, more cost efficient than increasing the number of samples usually.
I'm sorry, Arved.
Yeah.
Question. Do you have any numerical issues to compute this covariance matrix, its inverse, determinant?
For our examples, no, because we are in fairly small dimensions. Usually, Yeah, this is basically the only issue that we sometimes have, is that this is a normal distribution. So if we have prior distribution uniform, and then we use importance sampling with a normal distribution, we increase the sampling space, right? We can now, I mean, it's unlikely that we get samples outside of the prior, but it's not impossible. Normal samples can lie everywhere on the real line. And then if we have a sample, it could be non-physical, right? We could sample the vertical axis of the ellipse. And even though this is usually very concentrated covariance, it might happen that we get a negative thing here. And this makes no sense. Then our solver will complain, or our finite element solver will say, you're trying to create an ellipse with a negative axis. This doesn't work. So what we then have to use is instead use a truncated normal distribution.
Yeah, well, for example, one of issues which I see here is you have covariance matrix, but you compute this gradients approximately, and you may come to not symmetrical positive matrix, for example, or some eigenvalues could be small negative numbers.
I've actually never observed that. I read that, of course, if the density we're trying to approximate is already very concentrated, it's hard to find this maximum, right? Because basically you have almost a Laplace, a Dirac delta distribution, and then it's hard to find this maximum because the function will almost be zero everywhere, and also estimating the covariance, I assume. But I never encountered issues here.
Okay, thank you.
Okay. Okay, so now we come back to nested integrals. So everything for now was standard integral approximation. Now we have a nested integral in a standard form where we have one outer integral, a nonlinear function f, and then another integral. It's important that f is nonlinear. If f is linear, we could write both integrals as one larger dimensional integral, as I mentioned. In Monte Carlo or randomized quasi-Monte Carlo estimators, the dimension does not really play a role. So the issue really comes from this being nonlinear. And G also has to be a nonlinear relation between y and x. And then we have to use what we call nested estimators. The first one is the double loop. Yeah, so basically both the randomized quasi-Monte Carlo and the Monte Carlo estimator have the same shape again. We have outer samples n, the nonlinear function f, and then inner samples m. For the Monte Carlo estimator, those are random points. For the randomized quasi-Monte Carlo estimator, so same shape except that the points are randomized low discrepancy points. And so this estimator was introduced in previous work in 2003 by Ryan. This is the estimator that we introduced, and this is now, here it starts with our contribution. So I'm at the halfway point. Unfortunately, I have to speed up a bit, but basically here's what our contribution looks like. We use randomized quasi-Monte Carlo points for both the inner and the outer samples, and then we obtain error estimates. Okay, so for the double loop Monte Carlo estimator, this is as a reference, we have this finite element bias. We have the bias from the inner samples. So this is what it's all about, basically, with the nested integral. The inner integral, because of the nonlinearity of f, the outer integrand, we have a bias now. Usually Monte Carlo or randomized quasi-Monte Carlo's error estimators are unbiased. But for this nested structure, the inner one is still unbiased, but the outer one will have bias that is relative to the variance of the inner integrand. Now, this may sound a little strange or unintuitive, but basically, yeah, once we have a fixed number of inner samples, although it's unbiased, it will be off by some factor that is relative to the variance, and this adds bias to the outer Monte Carlo or randomized quasi-Monte Carlo estimator. And it also increases the variance a bit. So this is the regular variance of the outer Monte Carlo estimator, and this one comes from basically if we use the law of total variance, this comes from the inner discretization. But as we can see, if we let n and m go to infinity, this term is asymptotically not important. So what really increases the cost of the estimators is this bias. And now the optimal work is tolerance to the -3 plus gamma over eta. So before we had 2 plus gamma over eta. This comes from the finite elements. So we have a new factor of tall from this inner Monte Carlo sampling. And basically what this means is the if we want to reduce the error by 1/2, we need to increase the cost by a factor of 8 now. Before it was a factor of 4. So yeah, this is basically how the cost increases plus the finite element error, but this stays the same. Okay, for the randomized quasi-Monte Carlo estimator, we again have the finite element bias. The inner bias is reduced because the inner variance is reduced by this factor delta. And also in the variance, this delta appears. And now the outer variance is reduced by a factor beta. And beta and delta are assumed to be a bit different because, again, as I said, they depend on the dimension and also on the regularity of the integrand. And usually the outer, or for our examples of Bayesian design, the outer dimension will always be greater than the inner dimension. So this beta is assumed to be slightly less than 1 for our numerical experiments. We found that the delta will be close to 1. So the delta will be almost optimal. The beta is somewhere around 1/2 or something. Still better than using Monte Carlo here. And the optimal work is now given as tau to the -2 over 1 plus beta plus 1 over 1 plus delta, plus again the finite element contribution. So in the worst case, where beta and delta are 0, this is again tau to the -3. In the optimal case, where they are both 1, it's tau to minus 1.5. So using randomized quasi-Monte Carlo in both the outer and the inner discretization gives an improvement of 1.5 rate in the optimal case. So where does this leave us for the expected information gain, which is the basic criterion in the optimal experimental design? We want to approximate this. Just recall that this is the shape where we have the outer integral and then the logarithm and then the inner integral. With the double loop randomized quasi-Monte Carlo estimator. As I said, this first term is actually given in closed form. And this is because here we have the same theta as we have out here. So this is a Gaussian integral, we can solve it. So this is actually exact. But this one is the nested integral that we've seen, where we have the outer Monte Carlo or randomized quasi-Monte Carlo, the logarithm, and then the inner one. Okay, now we can also use importance sampling. Basically, we find a new measure from the Laplace approximation, pi tilde. So we approximate the posterior, and then we can sample from this. And this is possible because the posterior depends on the data observations, but we can sample those from the outer integral and then already use these samples before we do the inner integration. Yeah, and this is how the Laplace approximation of the posterior looks like. So here we have a theta hat is the map point, and the sigma is the covariance that we find. So it's basically the negative Hessian of the log likelihood, and it depends also, so it's evaluated at theta hat. Okay, here's our first actual numerical example. This is taken from a paper from Josef Marzouk, where he shows that here is some expected information gain with this kink here. And okay, what we can see here, this is a simple linear example, one-dimensional example. And for psi between 0 and 1, Yeah, on the left, we have the double loop Monte Carlo estimator. On the right, we have the double loop quasi-Monte Carlo estimator. For both estimators, we use 2 to the 15 outer points. This is roughly 30,000 points, and 1 inner point. This comes from the Laplace approximation. So as I said, this can be really powerful. And we actually did our error analysis. We obtained the optimal number of samples and saw that 1 inner sample is actually more than enough. So increasing the number of inner samples here would not decrease the error any more than increasing the number of outer samples. So this is why we have 2 to the 15 outer samples and 1 inner sample. But still, for Monte Carlo, this looks not ideal. So if we want to do an optimization here to find either this point or this point at the boundary, yeah, this would be challenging to optimize, whereas the randomized quasi-Monte Carlo looks very smooth, and this is what it's supposed to look like for the same number of points. So both of these also have roughly the same cost. There's a little extra cost associated with sampling or generating these low discrepancy points, but it's, for this example, it's negligible. Okay, and here we compare the cost of these estimators.
Sorry, question, Arved.
Yeah.
Sorry, Sanjay. In the previous plot, maybe I missed something. So here you are showing the expectation, and this rough or non-smooth behavior in the Monte Carlo is due to the high variance, I mean, because you are not showing maybe the confidence intervals. And I mean, any intuition why, I mean, you get the smooth behavior? Is it because you control the variance or something else?
Yeah, basically, I think what I did is I computed the optimal number of samples for a tolerance of 0.2 for Monte Carlo. And I think this is what I get, yeah. So basically, I use our optimal sampling scheme. I say, here is our error estimate. We run a pilot to estimate the variance of the Monte Carlo. We say, if I want a tolerance of 0.2, we need 15,000. We need 30,000 outer points, 1 inner point, and we get this plot, because error tolerance of 0.2 is not great. And then for comparison, I use the same number of points for randomized quasi-Monte Carlo. Does this answer your question, or do you have?
Yeah, I'm still like I'm looking what is the explanation why you get this smooth kind. I mean, again, this is expectation. One should understand it with some plus minus some standard deviations, right? I mean, and then any justification why or intuition why you get this smooth I mean, function for the expected information gain when you use QMC, randomized QMC.
Just because the randomized QMC has such a much smaller outer variance, right? So these are very close to the actual value of the function. So there's basically no variance here in every point. And here we have a variance of, yeah, these points differ from the true points by about a tolerance of 0.2. Of course.
Okay, thank you.
Yeah, if I used the same importance, the same optimal sampling scheme for the randomized quasi-Monte Carlo, we would also get a plot like on the left, but we would only have to use, I assume, 2 to the, I don't know, 6 points or something.
Thank you.
Okay, you're welcome. So yeah, here we compare the rates of the estimator for the previous example. So this is the where we use randomized quasi-Monte Carlo for the outer samples. And this is this is Monte Carlo for the outer samples. So we can see that the rate for the outer samples is drastically reduced compared to the Monte Carlo. So it's basically rate 1.09 compared to rate 2, which means it's almost optimal. Yeah, for the inner samples, we have rate 0.57 instead of rate 1. And again, 0.5 would be optimal here. Yeah, and then we have two more estimators that I didn't talk about, where we use the Laplace approximation directly. So then we don't have nested estimators. We can use the approximation of the posterior to get a non-nested estimator. So we only have one one Monte Carlo or one randomized quasi-Monte Carlo, and then we actually get the perfect rate for QMC at rate 1 instead of rate 2. But we have this bias from the Laplace approximation. Basically doing this second order Taylor introduces a bias that depends on what I previously called this constant P, if you remember, when I introduced the Laplace approximation. Here this T will basically be the number of experiments for us. So, and this is considered fixed because increasing the number of experiments is not like increasing the number of samples. It doesn't just add the computing cost, additional computing cost, but it actually means that we have to change the physical experiment. We have to run more experiments. This is usually not possible. So yeah, this is this Laplace bias here, and this is not seen in where we use Laplace approximation for importance sampling, because even though this importance sampling distribution will be not perfect, it does not add bias. Okay, and here is a consistency check. So we ran the estimator 100 times for several tolerances. And for a confidence of 95%, we expect this to be below the tolerance around 95% of the time. And it was below the tolerance almost all the time, which shows that for the double loop randomized quasi-Monte Carlo estimator, this estimate in the central limit theorem not only does it hold for a finite number of randomizations, but it's actually overly conservative. And we assume that this is because using only one inner sample because of importance sampling is already too much. But yeah, it may have other reasons also why this is so much below the tolerance. Okay, here's another example. Again, a physical example, thermoelasticity. We have a square domain. We have measurement sensors at the top that we can move around. This is our design. The red ones are to measure the temperature. The green ones are to measure the displacement. If we apply a heat source at this circular exclusion, the plate heats up and we can take measurements at the top, and we want to recover physical parameters, the thermal expansion coefficient, for example. So this is what it looks like. This is also a time-dependent problem. So we apply heat source, we wait a few seconds, and then the material heats up and we can pick up on this increased temperature. And here again, the same plot. So we have slightly worse QMC rates as for the linear example, where it was 1.09, I think, but basically this is still much better than the rate 2 of the Monte Carlo. And for the inner rate, we have 0.7 instead of 1. And if we use the Laplace approximation directly, we still get rate 2 for Monte Carlo and rate 1 for quasi-Monte Carlo. But here we also see that the Laplace approximation is not as good as before, where you see that the bias of the Laplace approximation is much larger. Okay, and this is what the optimal design looks like. Basically, the question we asked is, first of all, where do we put the sensors? And second of all, how long do we let the experiment run? So here we can see different sensor placements. The best one is where the sensors are close to the circular exclusion, as one would expect, but there's not much of a difference. What is interesting is that if we let the experiment not run long enough, we do not observe much in the sensors and we don't get optimal data. If we let it run for too long, basically the whole thing reaches a steady state, more or less. And basically everything is the temperature of the heat source. And then we also do not observe much anymore. So the best runtime for the experiment is somewhere in the middle. Yeah, and now I want to briefly, if I may, start the second part of my presentation, where we now consider a slightly more challenging problem. Because as many of you may know, if you have some elaborate model of some physical experiment, you not only have the design parameter that you get to choose, or the parameters of interest that you're interested in, you also have many other parameters. And some of these may be known exactly. So for example, the gravity constant or some other well-known constant, you can, of course, input as a fixed constant. But some of these may also be unknown. And usually what people do is they make a good guess and then use this guess, but then they neglect the uncertainty coming from these additional parameters, which we call nuisance parameters. And what you could also do is you could introduce also a distribution for these parameters and then recover them, like the parameters of interest. Then you just have a larger space for parameters of interest. This way you would be quantifying the uncertainty correctly, but you would not be solving the optimization problem that you want to solve, because you want to find the design xi that lets you optimally recover the parameters of interest and not all your other model parameters. So what you have to do instead is to marginalize the nuisance parameters. This way you're keeping track of the uncertainty and you are hopefully finding the optimal design just to recover the parameters of interest. And we write the likelihood now. Yeah, this is again the Gaussian distribution, but now it depends on theta and phi, where we introduce R, the data residual. But this is just for bookkeeping. What happens is, now that we've introduced these nuisance parameters, instead of one outer integral and one nested inner integral, we now have two inner integrals. But we can, again, in principle, use our estimators that we derived previously. Now we just have to use them twice, basically. So the posterior is now given as this marginalization over the likelihood, where before we had the marginalization only in the denominator. Now we have it in the numerator as well. And before the numerator was given in closed form, but now we instead have a nested integral. Okay, this is what the updated expected information gain looks like, where we have this now outer integral consisting of three parts: the logarithm, inner integral 1, logarithm, inner integral 2. And yeah, here this inner integral is only over the nuisance parameters, and here it's over nuisance parameters and the parameters of interest, because this was basically the evidence term. Okay, so now what do these nuisance parameters mean? For our physical example that I had at the beginning, the electrical impedance tomography, now we can, for example, say that the fiber angles are parameters of interest, and the vertical axis of this exclusion may be a nuisance parameter. Maybe we don't care. We just want to know about the fiber angles, but we know that somewhere, I'm sure all of you have applied this protective layer to your phone screens, and then it can happen that the air bubbles get trapped or something like this. So there may be this exclusion here. And yeah, you should model it, because otherwise you have uncertainty in your model that you're not keeping track of, but maybe you're only interested in these fiber angles. Okay, and now here's our contribution to this part. We use Laplace's method in a slightly more elaborate way here than we did before. So we use this for the marginalization of these nuisance parameters. Here is the posterior, again given by the likelihood over the evidence. This is the prior, sorry. Prior over evidence times likelihood. The likelihood is written as this. And this we write as the minus f function that we then use second order Taylor to approximate. And this gives this rather more complicated formula. Basically, we have this part over here is just dragging along. And then we can solve this Gaussian integral. But then we still have a nonlinear function, data residual, now of phi hat. It's the maximum of this likelihood only in phi. And this we call pi depending on phi hat. So this is the posterior with the nuisance parameters marginalized out by Laplace's method. But it's still a posterior, so we still need to approximate this. And yeah, phi hat is the minimum of this function f, only in phi. Okay, and then we use the Laplace approximation as we did before, because now we're back to where we were before with the posterior without nuisance parameters. And now theta hat is the argmax of this first Laplace's method approximation. And the covariance is basically the Hessian of this approximation. And from this, we obtain a non-nested estimator. Again, it's not so important what this looks like. What is important that we have one outer Monte Carlo and no inner discretization, only the bias from the Laplace approximation and the bias from the finite element approximation, but no inner sampling bias. And again, the problem is that the inner discretization bias we can usually get rid of by increasing the number of inner samples. We can usually not increase the number of experiments because it depends on external factors. Okay, so Eric, I'm not sure if at any point you would want to interrupt me, or but I would.
No, I mean maybe you can wrap up in like 5 minutes or so. Is that possible?
Okay. Yes, I think so. Should be. I have one more estimator, where instead I use, so forget about this previously derived elaborate Laplace approximation. Instead, we use regular Laplace approximation for importance sampling. So those are different Laplace approximations, but they are standard, basically. So these are the two Laplace approximations. They, yeah, those are the ones that are usually used. And yeah, we can use basically these Laplace approximations. The first one is for a fixed theta, because in the numerator, the theta was fixed. And then we can do Laplace approximation just to get an importance sampling distribution for phi. And for the denominator, we just write theta and phi as one higher dimensional vector, and we use the standard Laplace approximation. Okay, and then we can do importance sampling using these two for the numerator and denominator separately. Yeah, and so now here's an example for what nuisance parameters do. And this again comes from a paper from Yusuf Marzouk. So we have a trade-off here. Psi is our design. If we want to learn about theta, obviously we want to increase psi. If we want to learn about theta and psi, the optimal design clearly is at 1/2, given by this estimator. But if we only care about theta, then clearly the best design is at 1. So this shows what I introduced at the beginning, that marginalizing the nuisance parameters changes the expected information gain, and therefore changes the optimization function, the objective function when optimizing the design psi. Yeah, so even though if we recover both theta and phi, we get higher expected information gain, this basically doesn't matter because the optimal design we will find is not optimal when we just want to learn about the parameters of interest. And how much information we gain is basically not relevant. It's just important where we gain the maximum expected information for the thing we want to gain information about. Okay, here we again compare estimators. And yeah, here we can see that the outer number of samples basically doesn't change much if we use importance sampling, but the inner number of samples. So the green and the baseline are the inner number of samples without importance sampling. And here, these two lines are with importance sampling. So again, we can see how much they are reduced. Yeah, and this red line is the non-nested Laplace estimator, where we use this Laplace's method and then Laplace approximation. Here we don't have inner samples. And the variance of basically the outer samples here is reduced also a bit compared to the nested estimator. Yeah, and because the example is linear, we don't have a Laplace bias, but this is just okay. Yeah, here is the consistency check again, where we see that the double loop estimator is slightly over conservative, and the Monte Carlo estimator basically gives roughly 5 samples that are above the tolerance. Okay, and then for the electrical impedance tomography again, where we want to find the electrode placement. And now the vertical axis of the ellipse is the nuisance parameter. We find that if we recover both the fiber angles and the exclusion, we have a higher expected information gain. And the expected information gain also depends on the shift and the distance between electrodes. If we only want to recover the fiber angles, basically the expected information gain does not depend on the distance between the electrodes, only on the shift. And this is kind of intuitive. If you want to recover the fiber angles and you have no shift between electrodes, then you don't really get to see it. But for recovering the axis of the ellipse, also the distance between electrodes matter. Yes, that's it from my part. Thank you everyone for staying a bit longer. Here's where the funding came from. It is gratefully acknowledged. And here are some references for you.